Okay, welcome to Spring 2021 Pre-Calculus Lesson 3.3. We're going to do properties of logarithms today. Hopefully you've done the pre-test. We're going to talk about what a definition of logarithm is and use the basic definition to evaluate logarithms. And then we're going to talk about basic log properties that follow from the definition in this first video. This will be part one. All right, so the first thing you need to know about logarithm is it is the inverse. A logarithm is the inverse of the exponential. So what we have is a relationship between the exponential equation and a logarithmic equation. And this is the basic definition of a logarithm. If you have an exponential equation in the form b to the x equals a, you have one base of an exponent, and this base, b, has got to be greater than or equal to 0 and not equal to 1. Oops, greater than or equal to 0, not equal to 1. Trying a new computer here to see if I can write on it better than what I have before. If this is true, if you have this equation in this form, we have the exponential term isolated, then we say log base b of a equals x. This follows. If this is true, then this logarithmic expression is true. And if the logarithmic expression is true, this is true. So this allows us to convert an equation from exponential form to logarithmic form. If we have an equation in exponential form, 3 to the x equals 9. If we want to solve this for x, we can convert this from exponential form to logarithmic form by saying this is the log with the base is the same as the base of the exponent. And then what was on the other side of the equation from the exponential term goes inside. Oops, that was 3, not log. Not b. And then what was the exponent goes on the outside. And so log base 3 of 9 equals x. Well, you know from this simple equation that x has to equal 2. And that means that log base 3 of 9 is equal to 2. So when we look at this, now you need to recognize and see log base 3 of 9. I'm getting ahead of myself. We're going to do this to evaluate in just a little bit. Let's just convert for now. Convert these exponential equations. If I have a to the x equals 7, then we can convert that to logarithmic form and say as log base a of 7 equals x. If I have x to the second equals 4, we can write that and say log base x of 4 equals 2. So you can always convert from exponential form to logarithmic form, or vice versa. We can also go, that's what we just did, convert from exponential to logarithmic. We can also go from logarithmic to exponential. So if we had an equation that said log base 4 of x equals 16, then that implies if we go from logarithmic to exponential, we take the base of the logarithm, it becomes the base of the exponent, and then we raise that to the 16th power, whatever power was on the outside, or whatever number was on the outside becomes the power, and that equals what was inside the log. So if you have log base 2 of x equals 3, and we convert that to exponential form, it becomes 2 to the third equals x. This is how we convert from exponential to logarithmic form or logarithmic to exponential form. Now, when we use this to evaluate logarithms, let's look at what we had up there before, log base 3 of 9. If we set this equal to x and then solve that equation, we would have 3 to the x equals 9, so that x equals 2. Oops. That means that log base 3 of 9 is equal to 2. And so what I want you to see is that anytime you have the log base something of some number inside, what this log base b of m is asking us for, this is equal to the power of b that gives us m. So what power would you raise b to get m? That's the question you ask yourself when you're evaluating logarithm. We have log base 5 of 125. You're saying, what power of 5 gives me 125? Well, 5 times 5 is 5 squared. 5 times 5 is 25. Times 5 is 125. So 5 to the third power is equal to 125. And that's 3. We can look at a little more complicated examples. I'm going to add a page here. Let's look at a few more examples here like that. Let's say we have log base 4 of 0.25. Well, that's the same as log base 4 of 1/4, which is the same as log base 4 of 4 to the negative 1. That means that what power of 4 gives me 4 to the negative 1? That's just negative 1 power. So log base 4 of 0.25 is negative 1. There are some special bases. We talk about log base 10. I may be getting ahead of myself here, but we don't usually use the base. If you just see log 100, the implied and understood base is 10. So this is asking you, what power of 10 gives me 100? And you know that 10 to the second power gives you 100. So when you see log 100, where the base doesn't show, you know it's a base of 10. This is equal to 2. There's another special base, and we write this as ln of some number. We'll just say ln x. This means log base e of x. We never write this. We always write this if we're using log base e. So now you're wondering what e is. E is what's called the base of the natural logarithm. It's an irrational number, kind of like pi, 2.71828. Anyway, it goes on forever, never repeats. The base of the natural logarithm. It occurs in all sorts of physical phenomena. We use it a lot in advanced math. So we need to understand what B is, what E is, and we need to know that that's the base of the natural logarithm. So if you were asked to evaluate ln 3, this is equal to the power of the irrational number E that you raise it to give you 3. On your calculator, there is a log button. That's base 10. There's an ln button, and that's base E. Again, we never write log base E of x. We always write ln of x. Let's look at some things that follow from these basic log properties. If we have log base b of m is equal to log base b of n, this is asking you for the power of b that gives you m, and this is saying it's equal to the power of b that gives you n. So b to some power equals m, and b to some same power equals n. If those two b to the same powers are equal, then that power has to be equal. And it also means that m has to equal n. So whenever you see this, let's see if I find my eraser. Whenever you see log base b of m equals n, then this means that m is equal to n. So if I had, let's say, log base 3 of x plus 4 is equal to log base 3 of 2x minus 5, because the log bases are equal, I can drop them and get x plus 4 equals 2x minus 5. That means if I subtract x and I add 5 to both sides, I get x equals 9. And that would be the solution to the equation. But whenever the bases are equal, you can drop the logs and just say that m is equal to n. If we have log base b of 1, this is saying that what power of b that gives me 1. What power of b? Now remember from from earlier that b can't equal 0, has to be greater than 0, and it can't equal 1. If we had the log base 1, we would be saying 1 to what power equals what's inside. Well, if you raise 1 to any power, you get 1, so you can't really use 1 as a base of the logarithm. But any positive number not equal to 1 is what b has a candidate b. So if we're saying what power will we raise some b to some positive number, or b is some positive number, not 1. What power would I raise that to get 1? Well, we know from our properties of exponents that b to the 0 power equals 1. So this means that log base b of 1 is always equal to 0 for any valid base b. So if you had log base 3 of, say, x plus 2 equals 0, then we can convert that to exponential form and say that's 3 to the 0 equals x plus 2. Well, 3 to the 0 is just 1. And we subtract 2 from both sides, and we get x equals negative 1. Here we have log base b raised to b to the x power. Now, think about this. This is asking you what power of b equals b to the x power. Well, what goes in that question mark place has to be, x. So anytime you have log base b of b to the x power, the log base b cancels the b as the exponential and just gives you the exponent. So if we had an equation that said log of 10 to the 2x minus 5 equals 3. Well, the log and 10 as the base of the exponent cancel, gives you 2x minus 5 equals 3. So we add 5, get 2x equals 8, and divide by 2 and get x equals 4. Likewise, we have this property that says b to the log base b of x. Now think about this. This log base b of x is the power of b that gives you x. So if log base b of x is the power of b that gives you x, then b to the power that gives you x is just x. So again, the exponential as a base cancels the logarithm in the exponent, and this becomes just x. So if we had b, or let's do the number. Let's say we have e to the ln 5x minus 1 equals 5. Then we could say that e and the ln cancel each other. That leaves me 5x minus 1 equals 5. I add 1 to both sides, get 5x equals 6, and divide both sides by 5 and get x equals 6/5. That's part 1. Got some basic logarithmic properties, how we use them. We did some simple conversions of logarithms. We talked about the base e is the base of the natural logarithm, and the base 10 is the understood base when you don't see a base on the logarithm. And we talked about the definition of the logarithm, how to convert from exponential logarithmic form and logarithmic form to exponential form. And we used the definition to evaluate some logarithms. And we talked about how you cannot have x less than or equal to 0 as a base. The base can also not equal 1. You also can't have, we didn't talk about this yet, you can't have x equals 0 or x less than or equal to 0 inside the logarithm. Let's think about that real quick. If we had log base 2 of some negative number. That would be saying we're looking for a power that we can raise 2 to get a negative number. Now, if you raise 2 to a negative power, it becomes 1 over 2 to that positive power. So that's always a positive number. If you raise 2 to a 0, that gives you positive 1. That's a positive number. If you raise 2 to a positive power, that always gives you a positive power. So there's no power of 2 in the real numbers that you can raise, that you can get, that will give you a negative number. So we can't have a negative inside log. The same goes with 0. If we had log base 2 to the 0, we would be saying what power of 2 gives me 0. But we can't raise a positive number to a real number power and get 0, because even if we raise it to a negative number, it becomes 1 over 2 to that positive number, which is still a positive number. It can never be 0. So we can't have 0 or a negative number as the base of the logarithm or inside the log. And we'll talk more about that as we go through the study of logarithms. But that's part 1 of your lesson 3.3.